All right. Huh? 来点枪，怎么又进 ？Extend
不用眼镜
啊？
我下次你 stream。
OK。那我把 recording 关了。开始看一下，把 recording 关了。Okay. Yep. Do you have any questions?
Yeah, I have a question since I mentioned. Is it possible for you to schedule so that you go through the square for
Yeah, can you say it louder?
I was like, is it possible for you to schedule like something like a tutorial session and then you kind of go through the problem for
Okay, for the 5. Yeah, sure. I'm just planning to do a review section. If you want me to go through all the problems in your concept, then probably that's the way to go. Okay. Or also, I can go with the course material if you want. Yeah. So,
right, let's get started. So, we have 3 lectures left, including this one. I'm planning to finish all the course material this lecture, hopefully. So if that's the case, then we have 2 left. What I'm planning to do is I will devote maybe 1 or at least a half of 1 lecture to some other topics like you might be interested in, like Spark or NoSQL stuff, right? So maybe just the next lecture. Then at the very last lecture, I will go through, maybe I'll just go through all the problems in your problem written assignments so that you can get a review of the second half of this course, okay? So how does that sound, okay? And also our streaming is back home. I'm just recording the screen right now. Yeah, not recording this. It's just from the PC itself. So it might be actually. I think this way is better than you use a camera. It's easier to follow. But anyway, and project 5 is out, and I actually deleted all the B-tree related locking tests, so it will make your life a little bit easier. And also we have a deadline on December 9th, so it will leave you, I think, I would say plenty of time. But this time, if you don't make the deadline, I will not be able to grant any extension to that, okay? Because the schedule is really tight. Sorry about that. Regarding the test, the final exam, so as I said, it will only cover probably the content after the midterm. So starting from external sorting. Okay. So I guess I'll just remove all the parts involving extensible hashing and linear hashing. So I won't test on that. Just starting from external sorting and query optimizer, query execution, query optimization, transaction, concurrency control, crash recovery, and that's it for your test. Okay. And of course, in test there will be no nothing about NoSQL, Spark, which we'll cover a little bit next lecture if we do have time. But other than that, then that's about it. Okay. Okay. Let's continue with the lecture. So last time we finished with the predicate locking. I didn't have like a lot of time to talk about this, but the main idea of predicate locking is to solve the problem of phantom reads, right? So basically, if you have a transaction going on and read a range of things, like search for a range of stuff, and then somebody suddenly inserts something into that range which was not existent before and commit that that insertion. Then suddenly, when the first guy come back and search for the range again, he will find some phantom tuples that was not existent in the first search, right? So that's not a serializable schedule, and that's not a desirable phenomenon. So to solve that, we actually can use something called predicate locking. Basically, whenever you do a search, you have a predicate, whether it's a range or open-ended range or some sophisticated predicates. But the issue with that is predicate locking is quite expensive to maintain. Like if you have a log, if I say you have a log on arbitrary predicate, how do you actually check for that? Right? If I say I'm locking this range for updates, how do you check for that? Right? You have to evaluate the predicates for all log access, right? Whenever you ask for a log, whatever it is on, you have to check the general predicate, right? There's little opportunity to do any optimization, and it also like reduces the concurrency of your system. It's too expensive to maintain. So instead of that, typically we use something called the next key locking, which I talked about in last lecture. So basically, the next key locking is if you have a range, like if you have a B tree and you have two keys over here, and then there will be a gap between these two keys. So basically, let's say I can point on the screen. So let's say this key is 4. This key is 5. Okay. So if you are trying to insert 4 or 5 into the table, it could end up here, right? So if you are just doing this, then you could end up with phantom read. If I'm originally I'm searching for like a range of 3 to right. Suppose I'm searching for 3 smaller than or equal to x, smaller than or equal to 5, and then and you just scan the tuple of 5. Okay, here. So if somebody come in and insert a 4, it could end up here, right? End up here. So that's not something you want to do. So the way we handle that is we actually lock the gap here. There's a gap between the two keys. So there's a special kind of key. So typical implementation is actually lock the key itself and the next gap of it. So basically the way we implement that is when we lock this key, we no longer just get like a shared lock or exclusive lock. Instead, we basically grab a NS lock, something called NS lock. Okay, NS lock. The meaning of that is you lock the key itself and the gap after that. That's a way to understand this NS lock. Of course, sometimes you also have to lock the infinite range before all the keys. Sometimes like this, there's a gap before the first key. That's an infinite range. Sometimes you also need to lock that if you are searching for like something smaller than some number, right? So that's the general idea of NS key, but I'm not gonna dive into the details of that. Right. So that's the way to actually implement that. Okay, so finally, after all this discussion, we haven't really thought about deadlocks. Because in database systems, as I said, you do not have a choice in which order your access are coming in, right? So basically, your user can do whatever they want. They could be asking you to increment, let's say you increment the value of x, then y. And the other guy says increment the value of y, then x. That's a perfect example of deadlocks, right? If the two guys are the first guy does the increment of x, and the second guy at the same time does the increment of y, then suddenly they cannot get exclusive locks on both x and y, right? So then they get deadlocks. That's something you cannot easily avoid. So so in databases, we typically have two approaches to solve the problem. One is called deadlock prevention. The other is deadlock detection. Okay. So for deadlock prevention, we actually try to prevent any deadlocks. So how is that done? So basically, if somebody if TJ, transaction J, holds a lock, and TI wants to get the lock, you just disallow that. Okay, there are two possible schemes. Either you apply the wait die policy, which says if TI has a higher policy, then TI waits for J. Otherwise, TI aborts. Okay, so basically, if TI has a lower priority, it basically doesn't wait at all. It just aborts. Okay, so then suddenly, then in your wait graph, there cannot be any cycle, right? Because only transactions with higher priority can wait for the other transaction. Okay, so that means your wait for graph must be acyclic. Then you don't have since you do not have cycles, you do not have deadlocks. That's one way to do that. The other way to do that is called wound wait. That's to say if TI has a higher priority, instead of waiting, it just aborts the other transaction. Okay, that's sounds more like weird. Basically, if somebody with a higher priority and wants a lock, somebody else is holding, it can terminate the other transaction. Okay, or otherwise TI just wait. This is the same. So basically, you can only wait for a transaction if you have a lower priority in this case, right? So you still don't end up with any cycle in your wait for graph. So in this way, you can basically avoid deadlocks, but you do end up a bunch of spurious boards. Like you board for no reasons, right? Because like if you use wound wait and you are a transaction with a lower priority, and somebody suddenly wants your lock and you are boarded, right? So that's something really strange for here, but can it cause starvation? If you are not careful about the priorities, then it can cause starvation. But the key here is we basically assign priorities based on timestamps. Okay, so each transaction will have a start timestamp, and the older transaction will get a higher priority. Okay, that's based on the fact the observation that if transaction is older, that means it gets here first. That's something like a queue, right? If you are queuing for a shop, basically the first guy who came to the shop gets gets checked out first, right? So that's about it. So then you have to guarantee if some transaction gets aborted, then it will get its original timestamp when it gets retried. Okay. This way you can guarantee that if somebody is trying to do some transaction, it can eventually be committed or aborted, right? Just finish all the user logic. That's deadlock prevention. Yeah, I would say this is less usual than other things to implement in the system. But like it's a possible choice. Sometimes we just implement the deadlock prevention for the latches because the latches have a more like it's in the control of the programmer, the database developer, right? Not the end users. So if you are a database developer, you can somehow impose some ordering between the latches, and that's how you actually prevent deadlocks among the latches, but not really the locks. Sometimes people just use deadlock detection instead, because in detection you only run until you do have some deadlocks, right? So if you use prevention, sometimes it's not necessary for you to actually abort a transaction, but you could, because somebody suddenly wants to grab some logs some other people wants, right? So here for deadlock detection, you actually create a wait for graph. Okay, you can create a wait for graph, and the nodes are the transaction, and there's an edge from Ti to Tj. If Ti is waiting for Tj to release a log, Ti is wanting, okay, is requesting. And then you periodically check whether there's a cycle in the wait for graph. If there's a cycle, then you get a deadlock, right? So here's an example. Let's say we have this schedule here. Initially, T1 asked for a shared log on A and a shared log on D. Then T2 asked for a shared log on B. An exclusive log on B. At this moment, T1 asked for a shared log on B. So that will introduce a wait for relation between T1 and T2. That's the first edge here. Why it come from? So it's basically this wait. This is the first. Okay, and then at this time, the next is T3 asked for a shared log of D, which is actually granted because T1 actually just holds a shared log on D. Two transactions can hold a shared log on the same object at the same time. And then T3 asked for a shared log on C. That's also granted. Then T2 asked for an exclusive log on C here. So this will involve wait for relation. Basically, T2 is waiting for T3 here. That's where we have the second edge over here. Then if you continue with the process, basically T4 asks for an exclusive log on B, where T2 is still having an exclusive log on B, so that's a conflict. So basically that is a conflict. So here's the third wait for relation. And lastly, at this time, T3 asks for exclusive log on A, right? Because T1 has already is holding a shared log on A. That's not allowed. So this is a conflict. So basically, T3 will wait for that's the fourth, right? Oh, oops. So that's the fourth. You have the fourth edge over here, okay? And suddenly you find a cycle in the graph. It's like this. This is a cycle, okay? So basically, nobody can make progress until unless you kill them, right? So that's why it's a deadlock. However, in practice, although most systems do detection because they don't want to arbitrarily or unnecessarily abort transactions, but really maintaining the wait for graph is really expensive. Because as you see, for each log request, you have to update the graph. This is not a cheap operation to use. Like if you are just scanning a table, you have to update the graph for every read. Okay, that's not a good thing. So actually, practice shows that most wait for graph cycles are actually only length 2 or 3. Okay, basically you just have 3 guys waiting for each other or 2 guys waiting for each other. That's the most common thing. So hence, few transactions actually need to be aborted in practice. And so they basically they have different kinds of heuristics to get this implemented. Basically, you could just check for length 2 and length 3 cycles in your wait for graph. That's one possibility. And if that's the case, you only need to maintain maybe some partial information about the graph, right? And then, and also for length 2 and length 3 cycles, there are very efficient algorithms to actually find those cycles. It's not really expensive, but to find a cycle, like a cycle of arbitrary length, it's really expensive. Okay? You don't actually want to do that very often, like for each access or frequently, right? So that's the issue. There's also a timeout scheme where you just, if somebody is waiting for a log for a very long time, you just assume they are deadlocked. It's also safe, like you can basically abort anything in a database without doing any damage, although nobody is making progress, but that's fine. You can just arbitrarily abort something that's waiting for too long. Okay, so that's another approach to do deadlock detection instead of like constructing a wait for graph and checking for cycles. Okay, and it's a lot cheaper actually and works well in practice. But you do need to be very careful about the values you use in these schemes, so that you do not end up with too much aborts. Okay, too many aborts. All right, so that's about deadlocks. Any questions about deadlocks? Yep.
So what kind of timeout lengths typically work?
It's hard to say, depending on your workload. If your workload runs really fast and like in every second you commit like thousands or millions of transactions, then probably you just set it at maybe a second or half a second. I don't know, I just made up the number, but that maybe makes sense, right? But if you have a really long running transaction, it doesn't make sense for you to like arbitrarily abort that. Maybe it's just waiting for something and right. Okay, so then the last part, we actually just talk about logs a lot during in this discussion of concurrency control. But what are the latches? I think I mentioned a little bit, but I will give it a little bit more comparison between logs and latches. So basically, latches are the internal, like in-memory data structures, which are for synchronizations. Okay, it's basically you are trying to protect some in-memory data structure like hash table, linked list, or whatever like buffer pool, whatever manager you're using. So that's the purpose of latches. So they are purely in memory, and often the case, latches are implemented using system primitives like mutex, semaphore, something like that. But logs are different. Logs can work on arbitrary objects. It's not necessarily in memory. It can be on disk. It can be the tuples on the disk or a table, right? It can be abstract objects like gap between 2 keys, right? Or a predicate. So that's not something you can actually protect using a mutex or semaphore, right? So for logs, there's a component called log manager, which which provides an interface to get a log or release a log and check for whatever deadlocks you might have. So the common thing between logs and latches, they are both used to synchronize concurrent tasks. But logs are only for logical consistency. Basically, the concepts we mentioned in database, whatever like try to avoid all the bad anomalies we might encounter if we are running things in concurrent. But latches are actually used for physical consistency. By physical, this is basically in-memory data structures. Okay, so why treat them differently? So basically, there's a huge distinction between them. I would say this is actually one of the reasons database people like to reason about our data more so that's why we have a separate thing for locking them, right? So that's the lock. But for latches, it's basically implementation based. You just focus on the implementation. Sometimes you need synchronization among your critical sections. Then you need this kind of latches. So, but I think there's a more profound reason of that. Latches are obtained and released very often, and usually only for a very short period. Okay, that's just the usual case. Like if you are doing a concurrent B tree implementation, the chances that you are only gonna grab a latch on some page for a very short period. When you are searching for something, you just grab the latch on the root page for a little while, and when you land in its child page, you just release the latch on the root so that somebody else can actually search the root, right? But you do need logs on that, right? So if you sometimes you do need logs. Like if you are trying to update something, right? If you are trying to update a bunch of data records, and let's say you are still updating your B tree, okay? Maybe sometimes you update one of the data entry in one of your leaf, okay? So maybe you have released latch because you are finished with this data item, but you still cannot release the log on that, right? Otherwise, let's say two cases can happen if you release the log. If you do not have a log on some particular item, somebody can modify your uncommitted data or read your uncommitted data. That's dirty read, right? Or if you release the log prematurely, you have no chance to undo changes. Okay. So if you try to abort the transaction and you do not have the log, you cannot just go back and change that data. It could be an arbitrary state right now. Okay. So basically logs are really basically if you grab a log, it's gonna span the entire lifespan of your transaction. But latches can be released as soon as it's not needed. Okay. Yep.
Is there ever a latch without a lock?
Yes, there is the case. Like if you are traversing the B tree, often the case we do not lock the tuples. That's not related to your search. Okay, and yes, and also in a typical concurrent implementation, they also do not lock any of the pages or tuples. So that makes you wonder how they actually guarantee. So if you are doing a search for insertion, like you are search for insertion point, once you insert something, you might end up with like splitting things, right? So if you do not have a log, how can you go back and update those parent pages? So that's really tricky. So there's a variant of B tree called B-link tree, where basically when you are doing search, you can maintain a stack of the parent pages, but they are not locked and also not latched. So that means they can be changed during the course of your insertion, right? But when you go back, the B-link tree guarantees your actual parent page will not be on the left of the page you're keeping. Okay, so whatever split you are doing or merge you are doing, the actual page you want to find, the actual parent page you want to find must be on the right, either the one you are keeping in the stack or on the right of that page. So in that sense, you can basically search for that page if it's not really far away. Okay, and also like there are different schemes. Like the other scheme is basically you just search again. Okay, so if your parent page can end up with anywhere. Then basically, if you lose that page, you find this page is no longer the page you want. The page you keep in your stack is no longer the page you want. You can basically do a search again, okay, and try to locate that page. But in a good implementation, this should not happen very often, so that's fine. for that. Okay. Right. And also that there are actually a lot of log-free data structures like log-free B trees, like BW tree, this kind of stuff. What they are really saying is latch-free, not really log-free. It's not data logs, it's latches. Yeah, that's what it means. Okay, so here's a comparison. Basically, you have different things like the ownership of latches are going to belong to processes. But if you allow like a process to process many transactions and interleave transactions, then basically the logs does not have an affinity to any of these processes. It just belongs to certain transactions. And the duration of latches are short and the duration of logs are long. And we typically don't do any detection of deadlocks between latches. We just do prevention. But for logs, we typically check for deadlock detection. And overhead of latches are cheap. It's basically just a couple, maybe hundreds of instructions, tens of instructions actually. So for logs, it could be significantly larger, the cost. And the mode of latches are very simple. You just have shared or exclusive, right? And for logs, it's actually you have many more different modes. And there's no hierarchy in latches. You can just treat them as plain mutex, something like that, right? But logs can have a hierarchy. You have multi-granularity logs, and you can have different problems like log escalation, something like that, right? So that's the difference between them. Okay. So any questions about this? No? All right. So I'll finish this. So we're finished with the concurrency control. And the next part is actually called crash recovery. And let's first do a brief review of the assay property. Okay. So we have atomicity, consistency, isolation, and durability. So the question is that which ones needs the help of recovery manager? Okay, which ones needs the help of recovery? Yeah, which ones? Durability. Durability. Yeah, that's one of them. Anything else? Yeah, there's also atomicity. Okay, so basically, why atomicity needs that? Because sometimes if your effect is not reflected in whole in your database, then you probably need to redo things. Okay, we will see in just a minute. Okay, the motivation of that is basically you can have a bunch of transactions going on in your system, and it's committed or aborted or it's running. Okay. So suppose your system crashes at certain points, like here. If your system crashes, maybe because of power failure or hardware failure or your program have a bug, right? then basically it's killed by the operating system. Then it can crash. So atomicity says a transaction must be reflected in whole, either nothing or in whole, right? So that means if at the crash point, some of your changes hasn't gone to the disk, like here, like for let's say for this transaction, let's say only half of the effects has gone to the disk. You actually need to redo all the effects after that point, right? And also like here for the aborted transaction, if some of the effect has gone to the disk. You must undo those effects, right? You must not allow any of the effects of aborted transaction to be reflected on the disk, right? So that's why you need this kind of a recovery mechanism. Okay, so in this case, everything committed should be durable, and everything not committed or is still running at the time of crash should be aborted. Okay, so that means the effects should not be seen anywhere in your database. Okay, So let's make some assumptions. Let's say our concurrency control is in effect. That means we do use strict 2PL in this case. We do have strict 2PL in effect. That means you start grab locks in your transaction, and you do not release any lock until you commit the transaction. Okay, that's one of the basic assumptions. And then we say updates are happening in place. Basically, you do not do multi-version concurrency control. You just override the data over there. Okay. Can you think of a simple, very, very simple scheme without any logging that guarantees atomicity and durability? That's actually a very, very simple one, and it's the one you are implementing. Yes?
No steal and force.
Yeah, no steal and force, right. So basically, you that's also mentioned in your documents of project 5 and maybe 1, if I remember it correctly. So basically, the force policy means you make sure every update of your transaction is on the disk before you actually commit a transaction, okay, or declare a transaction as committed, okay. And the no steal policy says you do not allow the buffer pool with uncommitted updates to be evicted. Okay. So if something is has some page in your buffer pool has uncommitted data, that means it must be dirty, right? If it's evicted, then it will override the committed data on the disk, right? So you do not allow that. Basically, all uncommitted updates should not be on your disk. Okay, so this basically limits when we can actually write the data. That's at the commit time. You can only write anything at the commit time. Well, once something says, I want to start my commit process, you start writing things back to disk. Only at that time you write things back to disk. Other than that, you cannot do anything. Then this way, you do not need redo or undo. Of course, there are very nasty details like, what if your system crashed during writing things, right? What if you have a power failure or something like that? So there are really, really nasty details of that. But anyway, assuming if your disk writes are basically atomic, if that's provided by your operating system or somehow you have a layer to handle that, then these policies will work, right? Okay. But they are basically not preferred, right? Because it's really, really slow. You just write things at the end of each transaction. And so there are many cases where this is not desired because let's say your transactions happen in very high throughput, right? You have so many transactions in a short period of time. And also they are only touching a small amount of data. Okay, so they are basically just updating, say, a megabytes of data, but you do have a memory of gigabytes. Why bother like writing anything back to disk, right? You can purely do anything in memory because you have a buffer pool, right? So if you do use a force policy, then essentially for each of the transaction committed, you need to write things back to disk. It's gonna be slow, right? And also for no force, sometimes, like let's say your memory is scarce, right? And your working set is huge. What if all of your pages are dirty, right? Then basically you run out of memory and you cannot accept further transactions if you only allow no force, right? So that combination is not good. So actually what we want is called steal and no force. Okay, so the no force policy says you can like leave some of the dirty pages still in memory without writing the data back to the disk at the commit time. Okay, so you could basically write as little as possible. Like in the first example, if you have a very small working set that actually fits into buffer pool, you can basically write nothing, right? And you get pretty fast, like pretty high throughput. But this actually complicates the durability, right? Because sometimes if your system do crash, then your updates are lost. Okay. And you also have the steal policy, which says you can actually evict dirty pages. Okay, so you can overwrite committed data with uncommitted data. So that actually complicates atomicity. Why is that? Because sometimes some of the pages of your transaction could be evicted to the disk, but they are not committed yet. What if your system crashed at this point, right? So at this point, basically, some of the effects of one transaction is reflected on the disk, but some of them are not. You actually need to undo all those changes. Or even if you do not like have any crash, it also complicates the undo process. Like if you are trying to abort a transaction, some of the changes are on the disk, some are still in the memory. How do you actually undo those effects? So that the steal policy will complex the atomicity guarantee. Right? Okay, so basically we have 4 possible combinations between the 4 policies. Basically for steal and no steal and no force and force, you can basically mix and match. Okay? You can do whatever you want. So on the right hand, the upper right corner, you have the fastest possible buffer management policy. That's steal and no force. And force and no steal is the slowest one. Okay. So if you have a steal policy, then probably you need to do undo. Okay. So if you do have a steal policy, you will need to possibly you need to do undo. If you have a no force policy, then you probably need to do redo somewhere. Okay. So basically that's the relation between that. So if you have a no force and no steal policy, then since it's no force, basically you have a possibility to do redo. Okay. So that's why you have a you have a redo over here. And since you have a no steal policy, that means you never end up with an undo. So that means you do not need to do any undo over here. Okay. So basically that's how this matrix is formed. Okay. You just mix and match. So any questions so far about this part? Yep. Okay. Right. That's something you need to implement. Like just redo all the effects of certain transaction or undo all the effects of certain transaction, even if its effects is halfway there, okay, or nothing at all. Okay, that's the methods. Okay, so the general idea of implementing redo and undo. Let's say we're using the best possible policy, that's steal and no force. Then the basic idea is to use logging. Okay, logging is basically like you have a log, right? So you have a bunch of log records, which is an ordered list of redo and undo actions you might encounter during your database, during the execution of your database. So a log records will look like this. So this is something called, I think it's called value logging. Basically, you just record the values of your changes. Okay. So if you need redo, then you need to have new data for each operations in your database. Okay. If your operation changes some data, you need to record the new data for redo purpose. And if you need to do undo, then you need the old data part. Like basically, whenever you are trying to overwrite something, before that you copy the old data to your data record. That's the log. Okay, so let's see a very easy example. Okay, so let's say your transaction is updating a bunch of data records. Like if you have a transaction here and it's trying to write a tuple A and write a tuple B. Basically, you will have two log records. Okay, the first log records will have the old value of A in its old data part. Then you will have the new value of A. Okay, of A. That's the first log record. Then for the second log record, you will have the old value of B, okay, and the new value of B over here, okay. Let's say your database crashes before you actually write anything of this back to disk, okay, and the transaction is committed. What you do? You basically just scan all the all the log records here and write those new values again, right? So then you like basically make the effect of this transaction seen in the database, right? But what if you decide to abort the transaction, or the system just crash after you do these two writes, and the transaction is not committed yet? So that means this transaction cannot abort. You should not see any effects of this transaction. But if your new values are already flushed to the disk, then you probably need to write the old value to override the current values on your disk. Okay, so that's how you do the undo. Okay, so that's how you use the logs. Okay, and also there might be some additional control information that we will show later. Yeah.
When you have a transaction that depends on another transaction, but then the second one's committed, but the first one has to.
Right. So for strict 2PL, you actually don't end up with that. But like, of course, you could end up like some newer updates are reflected on the disk. Some older updates is also reflected on the disk, but they can like mix and match, right? So that's why we have a very complicated algorithm for that. So this is just a very simple example. If you just have like sequential execution of transactions, then this is the way you view that. But in reality, because you can have concurrent transactions, so the way you do redo and undo is more complicated than just like waving hands, right? Okay. Okay, so basically we require write-ahead logging. So the write-ahead logging protocol says you actually must force the log records to disk for an update before the corresponding data page gets to the disk. Okay, that ensures you actually can undo effects if you want. Okay, so that's still a point of force. So like you do not have you have no force policy in your buffer pool, but in the log manager you do need to force the log records before a certain data page gets to the disk. Okay, that's a point of force. And the other thing is you must force all the log records before a transaction actually commits. Okay, so that's also for the purpose of like redo and undo. Okay, so if you are missing some of the log records and your system crash, you might end up with a situation where you can not like redo the transaction, and then its effect could be torn, right? Only half of its effect is reflected on the disk. So that's the issue. So why this is okay? Why this is okay? We do not want no force on our buffer pool, but why can we do force in the log manager? Yeah, because it's small. Like if your transaction is small, then you do not write a lot of log records, then you probably will just be one IO. Like you can batch all of your log records into one IO and flush them to the disk. But for like buffer pool, you could be touching many of the database pages, right? And you flush them all. That's a lot of IO. Okay, so this is fine, but not fine to like have a force policy on buffer pool. Okay. And so exactly how is the logging and recovery? The most important part is how do we do recovery? How are they done? So we will look at the Aris algorithm from IBM, which is, I think, the original algorithm from the System R, right? So that's the very first relational database. So we will specifically look at the Aris algorithm, which is actually, I think, is still widely used today because, like, it's the way to do it. It's just the way to do it. Okay. So let's see what component we have in this. So basically, you do enforce the write-ahead logging in the system, and then each log record will have a unique log sequence number. it's just an incrementing number. Basically, the first log has a number of 1, the second log has a number of 2. 1, 2, 3, 4. That's the log sequence number. Of course, you could also do like 10, 20, 30. That's also up to your decision. But basically, the way you do that is basically you just increment the number every time. Okay, and then for each of the data page, like it could be a heap file page, it can be an index page, it can be internal or the leaf page, right? So for all these pages, you will have a page log sequence number, page LSN. That is the LSN of the most recent log records of that page, okay, of that page actually, right? So basically, if you update some page in your buffer pool, you need to update the page LSN of that page as well, okay? So that you can keep track of like what's the newest update in your page. And then the system also keeps track of flushed LSN. It's actually just an incrementing number as well. It marks the point where above which your log recs are all flushed to the disk. Okay, so basically your log sequence number could starting from 0, 1, 2, and so on. And at this point, say this is 40, then that basically means everything with LSN smaller than or equal to 40 are actually already on the disk. So that means if one of the page have a page LSN smaller than or equal to the flush LSN, then that page is eligible for eviction or write back. Okay. So what if the page LSN is larger than flush LSN? Then that means you cannot evict this page, or basically you cannot write back this page, because some of the records are updated, but its log record is not on the disk yet. Then you're violating the first force policy for the first rule of this write-ahead logging. Okay, so that's why you have this relation here. So basically, in general, the page LSN, all the flushed LSN will be like, of course, it's going to be smaller than or equal to the largest LSN in your system right now. Okay, that's the thing. And then for each of the log records, you will have these fields in your log. Basically, you will have a LSN of this log record, and then you will have a previous log LSN. The previous LSN of this log. So this is for the prev LSN is for like going back in history. If you are trying to undo stuff, you start from the latest change of this transaction and follow the prev LSN chain, and then you can find all the updates of this transaction. And then you also have a transaction ID, which indicates which transaction actually did this update. And then you have a type. Type could be update, commit, or abort. Of course, there are more types. There could be checkpoints, CLR for undo actions. This we will mention it a little bit later in more details. This is really important part of this for the ARIS algorithm to work. And also you could have an AND. So AND is a little bit weird. Like, why do you need an AND if you have commit and abort, right? That is because commit and abort can take a while to happen, right? Once you start a commit, this is actually start commit. If you are starting commit, you could like flush the log for a while, then you say end, right? And for abort, of course, you have a bunch of undos. During which course you actually need to write a bunch of CLRs, the compensation log records. So that actually you do need like a different LSN for the end. Okay. And then for the update records only, you need these other fields like page ID, which page you're changing, and offset, of course, and length is basically the length of the fields you are changing. Basically, if you have a page of page ID and it has an offset here, then the value you're setting is basically from offset to offset plus length. Okay, that's the range you're overriding. Okay, that's the range of bytes you're overriding. And then this before image is basically the old value on that page before you override the data. And the after the image is the new value, the value you actually write on the page in the buffer pool. Okay. So any questions about this part? The format of the log records. Okay, so let's continue. Okay, so there are some other log-related states. These are in-memory, purely in-memory state. You have two in-memory tables. One of the table is called a transaction table, where you have one entry per active transactions. So one transaction is active if and only if it has not been ended. Okay, that sounds weird, but it actually can have different status. A transaction could be just running. It doesn't say whether it's committing or aborting. Or it could be just started, commit, or abort, right? Those are different possibilities. Then for each of these entry, you will have a transaction ID, of course, to identify the transaction and the status. And also you have another important value called, the last LSA, okay? The last LSA is basically the most recent LSA written by this transaction. Okay, so that's basically the last update of this transaction. So if a transaction is running, then this probably is some update or begin transaction that log record. Or if it's committing or aborting, then probably this is commit record or the end record, right? So basically, it could be just the end record because it's trying to write that, right? Or something else. It could be other stuff. And then you have this 30-page table, DPT, which contains one entry per 30 page currently in the buffer pool. Okay, so its size will not exceed the size of the buffer pool, of course. So that's not a huge overhead, as you might think. So since the buffer pool is usually much smaller than your database size, so that's not a huge overhead for in-memory purpose. And then it will, for each of this entry, you will have a rec LSA, which is actually the first, log record that caused this page to be dirty. Okay, so this is really important. This needs to be the first one. Okay. This is just for redo and undo purpose. Okay, so if you do need the first such log record to properly do redo. Okay. Okay, so as in a big picture, so that's what we have. So basically, on the disk you have. Oh, I should point on the screen. So you have these log records, a bunch of log records, basically just a sequential file. Okay, you just append things to that file. And then you have a bunch of data pages, could be heap pages, index, internal pages, leaf pages, all kinds of stuff, whatever pages you have in the database. And each of them will have a page LSA. Okay, so that's also on the disk. This is on the disk, and this is also on the disk. But although they are in different files. And then you also have a master record. This master record we will mention in just a minute. It will contain some very important information for recovery purpose. Okay, and then in the memory, this is in memory. In the memory, you have some important values, like you have transaction table, you have 30-page table, and you have flushed LSA. Okay, that's the values you're using. Okay. So during the normal execution of a transaction, it's basically a series of reads and writes from the perspective of database, right? We only care about reads and writes. And that's followed by commit or abort, right? So we will assume the disk writes is actually atomic, okay? So in practice, additional details are needed to handle actually non-atomic writes. You could have tone writes, right? So these are really tricky to handle, but basically you could use like fflash to flash a disk, flash a certain file to the disk. Ask the system to actually flash the file to the disk. But until you get a response, you are not sure what state it's in, right? So that's one of the issue. But it's not. Let's just first assume our disk writes are atomic. That's beyond the problem of this algorithm. Okay. And then during the normal execution, we also enforce strict 2PL for concurrency control. And we use still and no force buffer pool management with write-ahead logging. Okay, so that's the normal execution of a transaction. And for transaction commit, when you are trying to commit a transaction, you write a commit record to the log, and then all the log records up to the transaction's commit record are flushed to the disk. Okay, so that makes you to guarantee that flushed LSN is greater than or equal to last LSN. Okay, so if something is committed, then you guarantee that the flush LSN is greater than or equal to last LSN. And then note that the log flushes are really sequential, so it's basically just synchronous writes. You just use fflush to write them back to the disk. Okay, and then you could have many log records, and potentially you have interleaving log records from different transactions. But that's okay. You just guarantee that your commit log record is actually on the disk. Then you're done. And then commit returns. Okay, the commit returns. About this end record, right. I feel this is, from my view, this is I don't really think this is necessary, right? So if your commit record is already on the disk, that means everything before this commit is also on the disk, right? So that means all of your all the log records for this particular transaction is already on the disk. So this end log records, I don't think it's really important for the commit purpose, unless you have some additional things to do during the transaction commit. Okay, so that's the way I view this end. So I don't think this is really important. Okay, but for abort, it does matter a lot. For abort, for now, let's just consider an explicit abort of the transaction. We do not have any crash, so our system is still doing a normal execution. Okay, so then we basically play back the log in reverse order. Okay, so what we get in the transaction table, we have the last LSN of a transaction. So that's where you made your last update during this transaction before your abort, right? So at this point, you can figure out what's the last LSN, right? And then you write an abort log, append an abort log to a log manager to say, hey, we want to abort this transaction, and also change the status in the transaction table to aborting. Okay, and then we basically can follow the chain of pre-LSN, right? We can follow the chain of pre-LSN to figure out what's the log records and start applying those before images to your buffer pool one by one, right? In reverse order. But most importantly, you do need to write a CLR, a compensation log record, for each of these undo operations. Okay. So let's say you have a bunch of writes. Let's say you have a log which is write A, write B, and write A, right? So what you do is actually you need to first find out the last LSN here, and then write an abort record over here. Okay. And sorry, at this point, you start undo the effect of this write A. Because you have a before image, you can basically apply that to your buffer pool. Then you basically write a CLR of, let's say this is 10, this is 20, 30, 40. Then this CLR will record something called 20. Okay, so basically it will record the prev LSing of the log record you are undoing. Okay. And in addition to that, basically because you are basically undo a thing, so you can keep a after image of your operation. In this case, the after image is actually the before image of write A, the log record of 30, right? And then you basically move to the next one. You are looking at the write B over here. So then you write a CLR 10. Which is the prev of this write B. And then you also, like, you have an after image, right? You have the after image, which is exactly the before image of 30, okay? And this is the same. Basically, this is the before image of 20, okay? And so on. And once you have finished all this undo operation, you have a bunch of CLR records. You write an AND to the disk, and try to flush them all you write an AND to the log records, and flush them all to the disk. Okay, and at this point, your transaction is officially aborted. You can basically return an abort message to the user, and also change the status of. You do not need to change status. Basically, just remove that entry for that transaction from the transaction table, and you're done. Okay. So so that's something I talk about in more details for a CLR record. While you are undoing, you basically you have one extra field than the normal log entry. This is called undo next LSing. That's the previous LSing of your undo operation. Okay, the previous LSing of the LSing you are trying to undo. And then CLR will only contain the redo information. That means it only contains the after image, but not the before image. Why is that? Because you never undo and undo. The reason is very tricky. It's like, why do we actually need to redo things? If our system never crashes, it never happens, right? But if our system do crash, then we probably need to redo some of the effects. But what if you are aborting something? You do not want that, right? So since you are aborting something, if something is still in progress, and you are redoing things, basically that transaction has no chance to finish. So that means that transaction needs to be rolled back anyway, right? And if something is just aborting, then it's abort. You have nothing to do. You just follow the decision to abort it, right? So you still need to undo that transaction, the original transaction. So a CLR record actually indicates you have reached the point where you finish some of the undo operation, but not the others, right? Okay, so these undo effects may on the disk, may not. Okay, but that doesn't matter. For our purpose, you never like undo that undo because you are still trying to undo that effect. Yeah, it's a little bit tricky to think about that. So the key thing here is once you decide to undo something, you never roll back that undo. Okay, so that's why you never need the undo information for a CLR record. So at the end of the day, once you have all the undos done and all the CLR records there, you write an AND to your log record and try to flush that to the disk. Okay, so that's how this abort works. Okay, so I see you might be confused about this CLR record, but as I will show you how actually we do recovery, you will immediately realize why they are useful. Okay, one more thing about checkpointing. Okay, so here the checkpointing we are mentioning here is something very lazy. It's a kind of lazy checkpointing. Basically, the purpose of checkpointing is that you do not want to go all the way back to the beginning of history of your database whenever your database crashes. Okay, so if you have done some work and your recovery, a lot of the effects are already on the disk, then you do not want to go all the way back in the history to like scan those, redo all those operations. So basically, periodically, you make a checkpoint so that you can roughly start from that point. Okay. So here, the definition of this checkpoint is quite lazy. Basically, it just records all the in-memory data structures. It just so whenever you try to do a checkpoint, you write a begin checkpoint record, indicates you have just started your checkpointing. Okay. And then you start collecting your transaction table and dirty table and write them into an end checkpoint record, okay, along with an end checkpoint record. At this point, you basically just write that end checkpoint to the disk, and at this point, you have a snapshot of all your in-memory data structures. And then, once you have that end checkpoint flashed to the disk, you store the LSA of the most recent checkpoint record in a safe place, which is the master record. Okay, so the master record is basically a very small file on your disk, which contains the LSA of the most recent succeeded checkpoint. Okay, so that's checkpointing. So what if we have a crash? If we do have a crash, we need to do a bunch of recovery, which involves a bunch of redos and undos. The way we do that is the big picture is shown as this. Basically, you start from the checkpoint found in your master records, which is the most recent checkpoint that has succeeded. Okay, and you start from that checkpoint. You just load the dirty page table and transaction table back to memory. Okay, and then you start analyzing all the transactions that are still running at the time of checkpoint. Okay, so notice that the analysis phase is actually could be like much before the like in history than the checkpoint. Okay, it could be like further involve more history than the most recent checkpoint. Why is that? Because if you have an ongoing transaction at the time point of checkpoint, the transaction could be still running and it could be just started from somewhere way back in the history. Okay, so that's where you might need to do some analysis, and some of the changes might not be on disk yet, right? So that's why if you do a lazy checkpoint, then that's the implication. And then basically you start from the oldest log records of transaction active at the crash point. I'm sorry. That's the oldest log record, but you actually don't start there. You find the smallest rec LSA in the dirty page table. Okay, so remember what was that? The rec LSA in the dirty page table is the first log LSA of each page, so that this LSA made a change to the page, so that it's 30, right? So that's the first point where your effect could be lost, right? So you find the smallest one of them, like here it's the smallest rec LSA in your dirty page table, and then so basically you start from there and start your redo over there. Okay. So let's talk about analysis phase a little bit more details. Okay. So we first need to re-establish the knowledge of state at the checkpoint. Okay, so basically you start from the log record, just over here. You start from the oldest log record to do the analysis, and then you basically just add things back to your transaction table and dirty page tables. Okay, so something different things can happen. Like during this course, some of the transactions could be like committed or aborted. Then basically, they will not be like in part of the transactions you might want to recover. But some of the transactions can actually still be running at the time of checkpoint. So that's something you actually need to keep in your transaction table. Okay. So for here, you basically start from the oldest transaction, and you start scanning forward the logs. And for an end record, you remove that transaction from your transaction table. Okay. And for other records, you basically add that particular transaction to your transaction table and set the last LSN of that transaction to the LSN you just found. And for each of the updates, you also potentially need to update the dirty page table and set the record LSN to that the first LSN you found for that table. For that page. So at the end of the day, the transaction table just says which transaction was still active at the time of crash, but it doesn't say anything about like. So potentially this transaction could be committed at the time of crash, but it's just the log records are not on the disk at this moment, right? It could be just the user says try to commit this transaction, and you start write a commit record to your log, but it hasn't gone to the disk, right? So, but since it's in progress, the user must have not seen the reply from your database. So that's okay to abort at this time, because once you say commit, it doesn't say anything that the database must commit it. The database still can abort the thing. And then the dirty page table will contain all the potential dirty pages at time of crash. It doesn't necessarily mean these pages are all dirty at the time of crash, because like some of the pages could still like be flushed during the course of last checkpoint and your crash. But it could also be the case that it's not, right? So it just says the dirty pages might not have made to the disk. It just says that. Okay. So for the sanity, you can basically try to undo the changes to those dirty pages if they are not committed yet. Okay. All right. Then you enter the redo phase. For redo, you basically just repeat the history to reconstruct the state at crash. So basically, you just apply all the updates, even of those aborted transactions, including those CLRs. Okay. So the way you do that is basically, if you have a transaction that's aborted, instead of just directly like go to the CLRs, you basically start from the begin transaction and start do those normal updates and apply them to your buffer pool. But once the transaction is aborted, it will start writing CLRs, right? So you start reapply the CLRs to your buffer pool again. Okay. So what's the after image of these CLRs? They are actually the before image of the corresponding updates. So this way you actually undo the effects. But why is this important? This is important because let's say you just have one transaction that's aborted in your database. You have a bunch of like something like write A, write B, and you have a abort, and you have a CLR of B, and a CLR of A, and you crash here. Of course you have an end here. So the way we do that is basically you first write the after image of this to disk, and write the after image of B to not to disk. Apply them to the buffer pool, and then you override the value of B here with the before image of B, and override the value of A in your buffer pool with the before, the before image of A, and which is the after image of the CR. Okay. Why do you want to do that? It can be the case that only some of the effects are actually on the disk. And it can also be in the case that some of the updates are not on the disk, and you can have interleaving transactions going on during the course, right? So it's not safe to assume it's in any valid state. So the only safe way to guarantee that it will revert back before the to the state before the transaction is actually do all the operations again. So it's like you have a bunch of operations and you end up with some certain state. You are not sure about what kind of state you have. Then you just redo all the operations again, so that you make sure you can be sure that you end up with a state that's essentially the same as if it's in normal execution. It never crashes. Okay, so that's why you do need to like apply this again. Okay, and then to redo an action, you just redo the logged action that's basically applied after image. And also you need to set the page LSN to LSN, okay, to the LSN, just updated the page, okay, so that you do not do any additional logging, you do not do any forcing. So basically after a crash, any recovery you've made may still be in the buffer pool and may still not on the disk, okay, so that's the thing. Right, I'm guessing I'm running out of time. So maybe I'll continue with redo and undo in the next lecture and give you a little bit example of that and finish everything, wrap up everything, and we will start talking about Spark next lecture. Okay, see you next time.